Imagine being Fernando Alonso, right?
Hmm.
You are strapped into a multi-million-dollar state-of-the-art Formula One machine, only to find yourself getting completely lapped at Suzuka. And why? Because your car is quite literally vibrating itself to pieces. Welcome to the deep dive.
Yeah, and we are going straight to the front lines today. Look, if you want to look past the race results and really understand the mechanical why behind the stopwatch, you are in the right place.
Exactly. Because we usually just talk about the Sunday spectacle. You know, the overtakes, the pit strategy, the podium champagne.
Right, the flashy stuff.
Right. But Formula One isn't just Sunday afternoon. It's a relentless, a vicious engineering war fought behind closed doors, in wind tunnels, and on simulation rigs. And today we are unpacking the brutal reality facing Aston Martin and Honda in the 2026 season.
It is absolute technical agony right now. We are talking about the physical destruction of the cars early in the season and these very specific, almost unorthodox strategic glimmers of hope that they are clinging to right now.
Okay, let's unpack this. Because to understand the trajectory of this team, we have to establish their baseline. And that baseline in the opening flyaway races in Australia, China, and Japan wasn't just, uncompetitive.
It was structurally destructive.
Exactly. Structurally destructive. We are talking about cars stuck in the garage, completely unable to complete running programs. Like, Lance Stroll's car spent huge portions of the Melbourne weekend just in pieces.
Yeah, and the primary issue wasn't a lack of aerodynamic downforce. The baseline issue was a power unit shaking the chassis so violently it was basically tearing itself apart.
Honda had a terrifying engineering crisis on their hands. You cannot develop aerodynamic performance when the fundamental architecture of the car is failing.
No, absolutely not. They had to utilize the April break before the Miami Grand Prix to bring a massive fundamental reliability upgrade. And look, the victory in Miami wasn't measured in championship points. Or even lap times, really.
What was it measured in then?
Just finished. Yes. The victory was simply that both cars crossed the finish line with zero battery vibrations. They finally cured the violent resonance that had been crippling the power unit.
But how did they actually achieve that under the intense pressure of a race calendar?
Yeah.
It wasn't just a software patch beamed over from a laptop, right?
Oh, not at all. They dedicated massive physical infrastructure to it. Honda literally left an actual chassis back at their Sakura facility in Japan.
Wait, an entire chassis just sitting in the factory?
An entire chassis. They strapped that car to a multi-axis test rig. It's basically this insane hydraulic platform that can simulate the physical forces of a racetrack, and they just ran relentless 24-hour simulations.
Wow.
They were hunting for the exact resonance frequency that was cracking the battery casings, because when an engine vibrates at the natural frequency of the surrounding carbon fiber and battery cells, the amplitude of that vibration multiplies until the material it fractures.
And Alonso was incredibly vocal about these vibrations from the cockpit, wasn't he?
Oh, furious. So Honda essentially dropped their immediate performance development to prioritize structural integrity. They just ran the rig until they isolated the frequency and engineered a dampening solution.
It's like trying to play a competitive, high-stakes first-person shooter on a top-tier PC, but your physical desk is shaking so violently you can't even hold the mouse to aim.
That is a perfect analogy.
Right. Like, you can have the best hardware in the world, but if the platform is unstable, the performance is zero. So Honda finally bolted the desk to the floor. They stopped the shaking. But here is the brutal reality of elite motorsport.
Bolting the desk doesn't make the game run at a higher frame rate.
Exactly. Finishing a race without breaking down does not mean you are fast.
Surviving the race just gives you the required data to see exactly how slow you actually are. And once the car stopped vibrating, the engineers could finally look at the cold, hard telemetry. And man, the data from Q1 in Miami paints a staggering picture of the deficit.
Let's put some numbers to that deficit because it is grim. In qualifying, the AMR26 was operating roughly 3.5 seconds off the pace of Mercedes.
3.5 seconds. In modern Formula One, that isn't just a gap. That is a completely different time zone.
It's a different zip code entirely. And when we compare their telemetry directly to Ferrari's SF26, Aston Martin lost 1.2 seconds in the corners alone. That breaks down to 0.8 seconds hemorrhaged in the slow corners and 0.45 seconds lost in the fast corners.
The high-speed corner deficit is the most alarming metric in that dataset. Honestly, it's terrifying.
Why specifically the high-speed corners?
Consider the track layout in Miami. There is really only one true sequence of high-speed corners, that sweeping complex through turns 4, 5, and 6. To lose nearly half a second to Ferrari in just one single sequence implies a massive aerodynamic flaw.
Just bleeding time.
Right. If you put the AMR 26 on a high-speed, load-demanding track like Silverstone or Suzuka, that mathematical deficit would multiply to the point where they are functionally racing in a different category.
Let's talk about the physics of that cornering loss. Because we aren't talking about the tires simply sliding on asphalt like, driving on a wet road. We're talking about airflow detachment.
Yes.
When a 2026 car pitches forward under heavy braking or rolls mid-corner, the floor, which generates the vast majority of the aerodynamic downforce, can suddenly lose its aerodynamic seal against the track surface.
The low-pressure suction just completely disappears.
Right. The aerodynamic load drops off an absolute cliff.
And that instantaneous loss of load is what destroys a driver's confidence. The car becomes entirely unpredictable. You also have to measure this against the midfield, by the way, not just the front runners.
Oh, like Alpine.
Exactly. Alpine was the undisputed leader of the midfield in Miami. Their car was incredibly efficient on the streets, literally pulling a full second on Aston Martin purely through top speed.
Full second on the straights. That's nuts.
It is. Yet Aston Martin was still bleeding time to Alpine in the corners, losing 0.2 between turns 1 and 3 and another 0.5 in the slow chicane.
Okay, wait. If the car is losing that much time in the corners because of airflow detachment and aerodynamic instability, why is Adrian Newey defending the chassis?
That is the million-dollar question.
Right, because internally, he considers the AMR 26 to be the 5th fastest chassis on the grid. He's essentially pointing the finger straight at the power unit. Yet Honda's track chief, SHINTARO ORIARA, claims their primary focus for the upcoming Canadian Grand Prix is to improve cornering speeds by tweaking the engine.
Yeah, ORIARA is hyper-focused on the engine.
But here's where it gets really interesting for me. How on earth does an engine fix an aerodynamic chassis problem?
It sounds like total contradiction, I know. But ORIARA's strategy for Montreal is deeply rooted in the mechanics of the 2026 regulations. The master plan isn't about bolting on raw horsepower to catch Alpine on the straights.
So what is it about?
It is entirely about drivability and energy management strategy. Because Honda lacked the extensive functional preseason testing data of Mercedes or Ferrari.
Because their car was stuck in the garage shaking itself apart.
Exactly. Because of that, their MGUK mapping is highly unrefined.
Okay, let's break that down for a second. The MGUK is the electric motor that harvests kinetic energy under braking and deploys it as torque during acceleration. If the mapping is unrefined, that torque delivery is harsh.
Very harsh. It acts like a light switch instead of a dimmer switch.
Right. If you dump a massive spike of hybrid power to the rear wheels mid-corner, right when the car is already aerodynamically unstable from that airflow detachment we just talked about, you completely overwhelm the rear tire's friction circle.
And the rear end instantly snaps out. You're facing backwards. So ORIARA's focus is on improving the precision of that torque delivery. If Honda can write better software to map the energy deployment so it comes on seamlessly, the driver isn't fighting a sudden surge of power.
So the engine mapping artificially masks the chassis' aerodynamic instability by keeping the rear tires within their grip limit.
You nailed it. It's an artificial patch.
That is wild. That smooth delivery gives Alonso and Stroll the confidence to carry, an extra 5 kilometers per hour into the apex?
Easily. They don't have to wait an extra fraction of a second to get back on the throttle because they trust the rear of the car isn't going to aggressively try to overtake the front. They are unlocking lap time purely for driver confidence generated by code.
And Montreal is the absolute perfect high-stakes laboratory to test this exact theory.
Oh, the circuit Gilles Villeneuve has a very specific profile. It demands perfect, sustained energy deployment down the massive back straight, followed by heavy, brutal braking zones into very slow corners like turns 1 and 2.
Not to mention, Canada historically brings cold, wet weather, which lowers the mechanical grip of the track surface to almost zero.
Exactly. In those conditions, if your MGUK delivers power aggressively, the car is going straight into the wall of champions. Do not pass go.
It's game over. And this strategy perfectly aligns with the human element, specifically with what Lance Stroll has been explicitly demanding from the engineering team.
Stroll has been very clear about this.
Very clear. He has stated he wants a car with an agile front end to attack the chicanes. But crucially, he needs and this is a quote, solid rear under heavy braking and combined entry.
That phrase right there, combined entry.
Yes. It is vital for anyone trying to understand car dynamics. It refers to the phase of the corner where the driver is trailing off the brake pedal while simultaneously turning the steering wheel toward the apex.
It is the most delicate, balanced transfer the car experiences in a lap.
Without a doubt, if the engine braking from the MGUK harvesting energy isn't perfectly synced and smooth, it completely upsets the car's pitch. Smooth engine torque provides the exact solid rear feeling he is begging for.
Look, Stroll's assessment here shows a remarkably high level of technical maturity. He knows precisely what the tool needs to do in that phase of the corner, and he is also actively managing the team's psychology.
Yeah, the mental side of this is huge.
Massive. Despite staring down the barrel of a 3.5-second deficit, he is refusing to let the garage spiral into panic. He actually points to the golden era Sebastian Vettel Red Bull cars.
Oh, the aerodynamic masterpieces designed by Adrian Newey that won 4 consecutive titles. Those exact ones. He uses them as the ultimate benchmark for a perfect car. Stroll's leaning on the fact that Aston Martin now employs Newey, and they possess a state-of-the-art factory. He believes the fundamental ingredients are there.
Trusting the process is a massive mental hurdle when you are getting lapped on a Sunday, though. I mean, fixing the MGUK torque delivery is a brilliant short-term band-aid for the chicanes in Montreal, but a software update doesn't generate downforce.
No, it doesn't.
What is the actual long-term strategic roadmap to close a 3.5-second gap? That requires physical development, which requires time, and it requires money.
It does. But the roadmap relies on a very specific regulatory lifeline buried in the 2026 rule set.
The AERODYNAMIC update.
Exactly. After the Canadian Grand Prix, Honda is in line for this AERODYNAMIC update. Under the new regulations, if an engine manufacturer is proven to be operating at a power deficit of more than 10% compared to the benchmark power unit on the grid, the FIA triggers an emergency parity mechanism. It's an organized lifeline, literally designed to prevent manufacturers from completely abandoning the sport when they get it drastically wrong.
Let's break down the mechanics of that concession, because it's huge.
First off, Honda will be granted significant extra hours on the dyno.
And for you listening right now who might be trying to picture this, a dyno, which is short for dynamometer, is essentially a highly sophisticated treadmill for an engine.
A treadmill from the future.
Exactly. You don't just put an engine on a table and rev it. You hook the power unit up to massive resistance motors that simulate the exact physical loads, the precise aerodynamic drag, and the specific gear shifts of a real lap around Silverstone or Monza.
It measures the power output down to the decimal without ever putting a physical car on the asphalt.
And those extra dyno hours are absolute gold dust. It allows them to run thousands of additional simulated laps to refine their energy deployment maps and safely push the combustion engine harder to find raw horsepower.
But the second part of the AERODYNAMIC concession is honestly even more critical: an increased budget allocation outside the standard cost cap. Wait. They are essentially granted permission to spend their way out of this horsepower deficit.
Yes, but how does a team practically spend their way out? I mean, it's not just buying a better turbocharger off a shelf.
No, it means hiring more specialized software engineers to write better energy algorithms. It means running more parallel test programs on those dynos.
Right. It means manufacturing dozens of incredibly expensive prototype components that they previously couldn't afford under the strict financial regulations.
And the FIA allows this because a severely uncompetitive engine manufacturer damages the overall competitive spectacle of Formula One. It makes for bad TV.
It really does. However, this raises an incredibly important question about the modern era of the sport. Do teams actually have the luxury of multi-year rebuilding phases anymore?
In the cost cap era.
Exactly. Even with extra dyno time and extra budget, designing, testing, and manufacturing new power unit components takes months. Stroll noted he doesn't want to be sitting on the sofa in 2 or 3 years when we start winning. He expects the turnaround to be aggressive.
But the laws of physics dictate that climbing out of a 3.5-second hole is a slow, agonizing process.
It's going to hurt.
So what does this all mean? Let's take a step back from the MGUK mapping and the AERODYNAMIC regulations for a second. I want you, listening right now, to think about a massive, overwhelming, long-term project you are tackling in your own life.
Something that feels mathematically insurmountable when you look at the end goal.
Exactly. You can't just skip to the finish line. You have to start by stabilizing your baseline. You have to stop the vibrations, even if it means halting your forward progress to fix the foundation.
Which is exactly what Honda did with that rig and Sacre.
Right. Then you have to look at the cold, hard data of your own deficits without ego. You have to trust the experts around you, rely on the grueling process, and fight for tiny increments of drivability and efficiency, trusting that those small adjustments will eventually compound into major gains. That is the reality of elite performance.
And Aston Martin and Honda are in the absolute trenches of that process right now. I mean, they survived a brutal start to the 2026 campaign. They diagnosed a critical destructive reliability flaw and cured it with brute force engineering.
And now they are walking into the unforgiving concrete walls of Montreal, armed not with a completely redesigned aerodynamic floor, but with heavily refined lines of engine code.
Yeah, they're relying almost entirely on software management and upcoming regulatory lifelines to bridge a canyon-sized gap to the front of the grid.
Which leaves us with a truly fascinating prospect for the future of motorsport. We are watching a team attempt to artificially synthesize aerodynamic grip and driver confidence using electric motor mapping.
I want to leave you with a final thought to really mull over. If software management, battery deployment algorithms, and simulated engine drivability can artificially compensate for a physically lacking aerodynamic chassis.
Are we rapidly entering an era where the millions of lines of code running inside the engine control unit are actually more important than the physical shape of the carbon fiber car itself?
It's a crazy thought.
Something to think about the next time you see a car snap out of a corner. We will see how Honda's code handles the heavy braking zones of Canada. Thank you for joining us on this deep dive. Keep questioning the why, and we'll catch you on the next one.